Iodine. Iodine is a chemical element with symbol I and atomic number 53. The heaviest of the stable halogens, it exists as a lustrous, purple-black non-metallic solid at standard conditions that sublimes readily to form a violet gas. The elemental form was discovered by the French chemist Bernard Courtois in 1811. It was named 2 years later by Joseph Louis Gay-Lussac from this property, after the Greek delta eta violet colored. Iodine occurs in many oxidation states, including iodide, iodate, and the various periodate anions. It is the least abundant of the stable halogens, being the 61st most abundant element. It is the heaviest essential mineral nutrient. Iodine is essential in the synthesis of thyroid hormones. Iodine deficiency affects about 2 billion people and is the leading preventable cause of intellectual disabilities. The dominant producers of iodine today are Chile and Japan. Iodine and its compounds are primarily used in nutrition. Due to its high atomic number and ease of attachment to organic compounds, it has also found favor as a non-toxic radiocontrast material. Because of the specificity of its uptake by the human body, radioactive isotopes of iodine can also be used to treat thyroid cancer. Iodine is also used as a catalyst in the industrial production of acetic acid and some polymers. In 1811, iodine was discovered by French chemist Bernard Courtois, who was born to a manufacturer of saltpetre. At the time of the Napoleonic Wars, saltpetre was in great demand in France. Saltpetre produced from French niter beds required sodium carbonate, which could be isolated from seaweed collected on the coasts of Normandy and Brittany. To isolate the sodium carbonate, seaweed was burned and the ash washed with water. The remaining waste was destroyed by adding sulfuric acid. Courtois once added excessive sulfuric acid and a cloud of purple vapor rose. He noted that the vapor crystallized on cold surfaces, making dark crystals. Courtois suspected that this material was a new element but lacked funding to pursue it further. Courtois gave samples to his friends, Charles Bernard Desormes and Nicolas Clement, to continue research. He also gave some of the substance to chemist Joseph Louis Gay-Lussac, and to physicist André-Marie Ampère. On November 29, 1813, Desormes and Clement made Courtois' discovery public. They described the substance to a meeting of the Imperial Institute of France. On December 6, Gay-Lussac announced that the new substance was either an element or a compound of oxygen. It was Gay-Lussac who suggested the name iode, from the Greek word omicron epsilon iota delta for violet. Ampère had given some of his sample to English chemist Humphrey Davy, who experimented on the substance and noted its similarity to chlorine. Davy sent a letter dated December 10 to the Royal Society of London stating that he had identified a new element. Arguments erupted between Davy and Gay-Lussac over who identified iodine first, but both scientists acknowledged Courtois as the first to isolate the element. In early periodic tables, iodine is often given the symbol J, for Jod, its name in German. Iodine is the fourth halogen, being a member of group 17 in the periodic table, below fluorine, chlorine, and bromine. It is the heaviest stable member of its group. Iodine has an electron configuration of 4d105s25p5, with the 7 electrons in the fifth and outermost shell being its valence electrons. Like the other halogens, it is 1 electron short of a full octet and is hence a strong oxidizing agent, reacting with many elements in order to complete its outer shell. Although in keeping with periodic trends, it is the weakest oxidizing agent among the stable halogens. It has the lowest electronegativity among them, just 2.66 on the Pauling scale. Elemental iodine hence forms diatomic molecules with chemical formula I2, where 2 iodine atoms share a pair of electrons in order to each achieve a stable octet for themselves. At high temperatures, these diatomic molecules reversibly dissociate a pair of iodine atoms. Similarly, the iodide anion, I, is the strongest reducing agent among the stable halogens, being the most easily oxidized back to diatomic I2. The halogens darken in color as the group is descended. Fluorine is a very pale yellow gas, chlorine is greenish yellow, and bromine is a reddish-brown volatile liquid. Iodine conforms to the prevailing trend, being a shiny black crystalline solid that melts at 114 degrees C and boils at 183 degrees C to form a violet gas. This trend occurs because the wavelengths of visible light absorbed by the halogens increase down the group. Specifically, the violet color of iodine gas results from the electron transition between the highest occupied antibonding πg molecular orbital and the lowest vacant antibonding sigma u molecular orbital. Elemental iodine is slightly soluble in water, with 1 gram dissolving in 3450 ml at 20 degrees C and 1280 ml at 50 degrees C. Potassium iodide may be added to increase solubility via formation of triiodide ions, among other polyiodides. Nonpolar solvents such as hexane and carbon tetrachloride provide a higher solubility. Polar solutions, such as aqueous solutions, are brown, reflecting the role of these solvents as Lewis bases. On the other hand, nonpolar solutions are violet, the color of iodine vapor. Charge transfer complexes form when iodine is dissolved in polar solvents, hence changing the color. Iodine is violet when dissolved in carbon tetrachloride and saturated hydrocarbons but deep brown in alcohols and amines, solvents that form charge transfer adducts. The melting and boiling points of iodine are the highest among the halogens, conforming to the increasing trend down the group, since iodine has the largest electron cloud among them that is the most easily polarized, resulting in its molecules having the strongest van der Waals interactions among the halogens. Similarly, iodine is the least volatile of the halogens. Because it has the largest atomic radius among the halogens, iodine has the lowest first ionization energy, lowest electron affinity, lowest electronegativity, and lowest reactivity of the halogens. The interhalogen bond in diiodine is the weakest of all the halogens. As such, 1% of a sample of gaseous iodine at atmospheric pressure is dissociated into iodine atoms at 575 degrees C. Temperatures greater than 750 degrees C are required for fluorine, chlorine, and bromine to dissociate to a similar extent. Most bonds to iodine are weaker than the analogous bonds to the lighter halogens. Gaseous iodine is composed of I2 molecules with an II bond length of 266.6 pm. The II bond is one of the longest single bonds known. It is even longer in solid orthorhombic crystalline iodine, which has the same crystal structure as chlorine and bromine. As such, within the iodine molecule, significant electronic interactions occur with the two next nearest neighbors of each atom, and these interactions give rise, in bulk iodine, to a shiny appearance and semiconducting properties. Iodine is a two-dimensional semiconductor with a band gap of 1.3 eV. It is a semiconductor in the plane of its crystalline layers and an insulator in the perpendicular direction. Of the 37 known isotopes of iodine, only one occurs in nature, iodine-127. The others are radioactive and have half-lives too short to be primordial. As such, iodine is monoisotopic and its atomic weight is known to great precision, as it is a constant of nature. The longest-lived of the radioactive isotopes of iodine is iodine-129, which has a half-life of 15.7 million years, decaying via beta decay to stable xenon-129. Some iodine-129 was formed along with iodine-127 before the formation of the Solar System, but it has by now completely decayed away, making it an extinct radionuclide that is nevertheless still useful in dating the history of the early Solar System or very old groundwaters, due to its mobility in the environment. Its former presence may be determined from an excess of its daughter xenon-129. Traces of iodine-129 still exist today, as it is also a cosmogenic nuclide, formed from cosmic ray spallation of atmospheric xenon. These traces make up 1014 to 1010 of all terrestrial iodine. It also occurs from open-air nuclear testing, and is not hazardous because of its incredibly long half-life, the longest of all fission products. At the peak of thermonuclear testing in the 1960s and 1970s, iodine-129 still made up only about 10.7 of all terrestrial iodine. Excited states of iodine-127 and iodine-129 are often used in Mossbauer spectroscopy. The other iodine radioisotopes have much shorter half-lives, no longer than days. Some of them have medical applications involving the thyroid gland, where the iodine that enters the body is stored and concentrated. Iodine-123 has a half-life of 13 hours and decays by electron capture to tellurium-123, emitting gamma radiation. It is used in nuclear medicine imaging, including single-photon emission computed tomography and X-ray computed tomography scans. Iodine-125 has a half-life of 59 days, decaying by electron capture to tellurium-125 and emitting low-energy gamma radiation, the second longest-lived iodine radioisotope. It has uses in biological assays, nuclear medicine imaging and in radiation therapy as brachytherapy to treat a number of conditions, including prostate cancer, uveal melanomas, and brain tumors. Finally, Iodine-131, with a half-life of 8 days, beta decays to an excited state of stable xenon-131 that then converts to the ground state by emitting gamma radiation. It is a common fission product and thus is present in high levels in radioactive fallout. It may then be absorbed through contaminated food, and will also accumulate in the thyroid. As it decays, it may cause damage to the thyroid. The primary risk from exposure to high levels of iodine-131 is the chance occurrence of radiogenic thyroid cancer in later life. Other risks include the possibility of non-cancerous growths and thyroiditis. The usual means of protection against the negative effects of iodine-131 is by saturating the thyroid gland with stable iodine-127 in the form of potassium iodide tablets, taken daily for optimal prophylaxis. However, iodine-131 may also be used for medicinal purposes in radiation therapy for this very reason, when tissue destruction is desired after iodine uptake by the tissue. Iodine-131 is also used as a radioactive tracer. Though it is the least reactive of the halogens, iodine is still one of the more reactive elements. For example, while chlorine gas will halogenate carbon monoxide, nitric oxide, and sulfur dioxide, iodine will not do so. Furthermore, iodination of metals tends to result in lower oxidation states than chlorination or bromination. For example, rhenium metal reacts with chlorine to form rhenium hexachloride, but with bromine it forms only rhenium pentabromide, and iodine can achieve only rhenium tetraiodide. By the same token, however, since iodine has the lowest ionization energy among the halogens and is the most easily oxidized of them, it has a more significant cationic chemistry and its higher oxidation states are rather more stable than those of bromine and chlorine, for example in iodine heptafluoride. The simplest compound of iodine is hydrogen iodide, Hi. It is a colorless gas that reacts with oxygen to give water and iodine. Although it is useful in iodination reactions in the laboratory, it does not have large-scale industrial uses, unlike the other hydrogen halides. Commercially, it is usually made by reacting iodine with hydrogen sulfide or hydrazine. At room temperature, it is a colorless gas, like all of the hydrogen halides except hydrogen fluoride, since hydrogen cannot form strong hydrogen bonds to the large and only mildly electronegative iodine atom. It melts at 51.0 degrees C and boils at 35.1 degrees C. It is an endothermic compound that can exothermically dissociate at room temperature. Although the process is very slow unless a catalyst is present, the reaction between hydrogen and iodine at room temperature to give hydrogen iodide does not proceed to completion. The Hi bond dissociation energy is likewise the smallest of the hydrogen halides, at 295 kJ/mol. Aqueous hydrogen iodide is known as hydroiodic acid, which is a strong acid. Hydrogen iodide is exceptionally soluble in water. 1 liter of water will dissolve 425 liters of hydrogen iodide, and the saturated solution has only 4 water molecules per molecule of hydrogen iodide. Commercial so-called concentrated hydroiodic acid usually contains 48-57% high by mass. The solution forms an azeotrope with boiling point 126.7 degrees C at 56.7 G high per 100 G solution. Hence hydroiodic acid cannot be concentrated past this point by evaporation of water. Unlike hydrogen fluoride, Anhydrous liquid hydrogen iodide is difficult to work with as a solvent, because its boiling point is low, it has a small liquid range, its dielectric constant is low and it does not dissociate appreciably into H2 and high 2 ions. The latter, in any case, are much less stable than the bifluoride ions due to the very weak hydrogen bonding between hydrogen and iodine, though its salts with very large and weakly polarizing cations such as Cs and Nr+4 may still be isolated. Anhydrous hydrogen iodide is a poor solvent, able to dissolve only small molecular compounds such as nitrosyl chloride and phenol, or salts with very low lattice energies such as tetralkylammonium halides. Nearly all elements in the periodic table form binary iodides. The exceptions are decidedly in the minority and stem in each case from one of three causes: extreme inertness and reluctance to participate in chemical reactions, extreme nuclear instability hampering chemical investigation before decay and transmutation, and having an electronegativity higher than iodines, so that the resultant binary compounds are formally not iodides but rather oxides, nitrides, or halides of iodine. Given the large size of the iodide anion and iodine's weak oxidizing power, high oxidation states are difficult to achieve in binary iodides, the maximum known being in the penta-iodides of niobium, tantalum, and protactinium. Iodides can be made by reaction of an element or its oxide, hydroxide, or carbonate with hydroiodic acid, and then dehydrated by mildly high temperatures combined with either low pressure or anhydrous hydrogen iodide gas. These methods work best when the iodide product is stable to hydrolysis. Otherwise, the possibilities include high-temperature oxidative iodination of the element with iodine or hydrogen iodide, high-temperature iodination of a metal oxide or other halide by iodine, a volatile metal halide, carbon tetraiodide, or an organic iodide. For example, molybdenum oxide reacts with aluminium iodide at 230 degrees C to give molybdenum iodide. An example involving halogen exchange is given below, involving the reaction of tantalum chloride with excess aluminium iodide at 400 degrees C to give tantalum iodide. Lower iodides may be produced either through thermal decomposition or disproportionation, or by reducing the higher iodide with hydrogen or a metal, for example. Most of the iodides of the pre-transition metals are mostly ionic, while nonmetals tend to form covalent molecular iodides, as do metals in high oxidation states from +3 and above. Ionic iodides Min tend to have the lowest melting and boiling points among the halides Mxn of the same element, because the electrostatic forces of attraction between the cations and anions are weakest for the large iodide anion. In contrast, covalent iodides tend to instead have the highest melting and boiling points among the halides of the same element, since iodine is the most polarizable of the halogens and, having the most electrons among them, can contribute the most to van der Waals forces. Naturally, exceptions abound in intermediate iodides where one trend gives way to the other. Similarly, solubilities in water of predominantly ionic iodides are the greatest among ionic halides of that element, while those of covalent iodides are the lowest of that element. In particular, silver iodide is very insoluble in water and its formation is often used as a qualitative test for iodine. The halogens form many binary, diamagnetic interhalogen compounds with stoichiometries XY, XY3, XY5, and XY7, and iodine is no exception. Iodine forms all three possible diatomic interhalogens, a trifluoride and trichloride, as well as a pentafluoride and, exceptionally among the halogens, a heptafluoride. Numerous cationic and anionic derivatives are also characterized, such as the wine red or bright orange compounds of ICl+2 and the dark brown or purplish-black compounds of I2Cl+. Apart from these, some pseudohalides are also known, such as cyanogen iodide, iodine thiocyanate, and iodine azide. Iodine monofluoride is unstable at room temperature and disproportionates very readily and irreversibly to iodine and iodine pentafluoride, and thus cannot be obtained pure. It can be synthesized from the reaction of iodine with fluorine gas in trichlorofluoromethane at 45 degrees C, with iodine trifluoride in trichlorofluoromethane at 78 degrees C, or with silver fluoride at 0 degrees C. Iodine monochloride and iodine monobromide, on the other hand, are moderately stable. The former, a volatile red-brown compound, was discovered independently by Joseph Louis Gay-Lussac and Humphrey Davy in 1813, for not long after the discoveries of chlorine and iodine, and it mimics the intermediate halogen bromine so well that Justus von Liebig was misled into mistaking bromine for iodine monochloride. Iodine monochloride and iodine monobromide may be prepared simply by reacting iodine with chlorine or bromine at room temperature and purified by fractional crystallization. Both are quite reactive and attack even platinum and gold, though not boron, carbon, cadmium, lead, zirconium, niobium, molybdenum, and tungsten. Their reaction with organic compounds depends on conditions. Iodine chloride vapor tends to chlorinate phenol and salicylic acid, since when iodine chloride undergoes homolytic dissociation, chlorine and iodine are produced and the former is more reactive. However, iodine chloride in tetrachloromethane solution results in iodination being the main reaction, since now heterolytic fission of the ICl bond occurs and and attacks phenol as an electrophile. However, iodine monobromide tends to brominate phenol even in tetrachloromethane solution because it tends to dissociate into its elements in solution, and bromine is more reactive than iodine. When liquid, iodine monochloride and iodine monobromide dissociate into I2X and N9,2 anions, thus they are significant conductors of electricity and can be used as ionizing solvents. Iodine trifluoride is an unstable yellow solid that decomposes above 28 degrees C. It is thus little known. It is difficult to produce because fluorine gas would tend to oxidize iodine all the way to the pentafluoride. Reaction at low temperature with xenon difluoride is necessary. Iodine Tri Chloride, which exists in the solid state as the planar dimer I2Cl6, is a bright yellow solid, synthesized by reacting iodine with liquid chlorine at 80 degrees C. Caution is necessary during purification because it easily dissociates to iodine monochloride and chlorine and hence can act as a strong chlorinating agent. Liquid iodine trichloride conducts electricity, possibly indicating dissociation to ICl+2 and ICl4 ions. Iodine Pentafluoride, a colorless, volatile liquid, is the most thermodynamically stable iodine fluoride, and can be made by reacting iodine with fluorine gas at room temperature. It is a fluorinating agent, but is mild enough to store in glass apparatus. Again, slight electrical conductivity is present in the liquid state because of dissociation to If+4 and If6. The pentagonal bipyramidal iodine heptafluoride is an extremely powerful fluorinating agent, behind only chlorine trifluoride, chlorine pentafluoride, and bromine pentafluoride among the interhalogens. It reacts with almost all the elements even at low temperatures, fluorinates Pyrex glass to form iodine oxyfluoride, and sets carbon monoxide on fire. Iodine oxides are the most stable of all the halogen oxides, because of the strong IO bonds resulting from the large electronegativity difference between iodine and oxygen, and they have been known for the longest time. The stable, white, hygroscopic iodine pentoxide has been known since its formation in 1813 by Gay-Lussac and Davy. It is most easily made by the dehydration of iodotic acid, of which it is the anhydride. It will quickly oxidize carbon monoxide completely to carbon dioxide at room temperature, and is thus a useful reagent in determining carbon monoxide concentration. It also oxidizes nitrogen oxide, ethylene, and hydrogen sulfide. It reacts with sulfur trioxide and peroxidisulfuryl difluoride to form salts of the iodyl cation, plus, and is reduced by concentrated sulfuric acids to iodosyl salts involving plus. It may be fluorinated by fluorine, bromine trifluoride, sulfur tetrafluoride, or chloryl fluoride, resulting iodine pentafluoride, which also reacts with iodine pentoxide, giving iodine oxyfluoride, IOF3. A few other less stable oxides are known, notably I409 and I2O4. Their structures have not been determined, but reasonable guesses are III and plus respectively. More important are the four oxoacids: hypoiodous acid, iodous acid, iodic acid, and periodic acid. When iodine dissolves in aqueous solution, the following reactions occur. Hypoiodous acid is unstable to disproportionation. The hypoiodite ions thus formed disproportionate immediately to give iodide and iodate. Iodic acid and iodide are even less stable and exist only as a fleeting intermediate in the oxidation of iodide to iodate, if at all. Iodates are by far the most important of these compounds, which can be made by oxidizing alkali metal iodides with oxygen at 600 degrees C and high pressure, or by oxidizing iodine with chlorates. Unlike chlorates, which disproportionate very slowly to form chloride and perchlorate, iodates are stable to disproportionation in both acidic and alkaline solutions. From these, salts of most metals can be obtained. Iodic acid is most easily made by oxidation of an aqueous iodine suspension by electrolysis or fuming nitric acid. Iodate has the weakest oxidizing power of the halates, but reacts the quickest. Many periodates are known, including not only the expected tetrahedral Io4, but also square pyramidal Io3-5, octahedral orthoperiodate Io5-6, 2, 4, and I2049. They are usually made by oxidizing alkaline sodium iodate electrochemically oxide as the anode, or by chlorine gas. They are thermodynamically and kinetically powerful oxidizing agents, quickly oxidizing Mn2+ to MnO4, and cleaving glycols, alpha-diketones, alpha-ketols, alpha-amino alcohols, and alpha-diamines. Orthoperiodate especially stabilizes high oxidation states among metals because of its very high negative charge of 5. Orthoperiodic acid, H5IO6, is stable, and dehydrates at 100 degrees C in a vacuum to metaperiodic acid, HiO4. Attempting to go further does not result in the non-existent iodine heptoxide, but rather iodine pentoxide and oxygen. Periodic acid may be protonate by sulfuric acid to give the I+6 cation, isoelectronic to Te6 and Sb6, and giving salts with bisulfate and sulfate. When iodine dissolves in strong acids, such as fuming sulfuric acid, a bright blue paramagnetic solution including I+2 cations is formed. A solid salt of the diiodine cation may be obtained by oxidizing iodine with antimony pentafluoride. The salt I2Sb2F11 is dark blue, and the blue tantalum analog I2Ta2F11 is also known. Whereas the II bond length in I2 is 267 pm, that in I+2 is only 256 pm as the missing electron in the latter has been removed from an antibonding orbital, making the bond stronger and hence shorter. In fluorosulfuric acid solution, deep blue I+2 reversibly rises below 60 degrees C, forming red rectangular diamagnetic I2+4. Other polyiodine cations are not as well characterized, including bent dark brown or black I+3 and centrosymmetric C2H green or black I+5, known in the ASF6 and AlCl4 salts among others. The only important polyiodide anion in aqueous solution is linear triiodide, I3. Its formation explains why the solubility of iodine in water may be increased by the addition of potassium iodide solution. Many other polyiodides may be found when solutions containing iodine and iodide crystallize, such as I5, I9, I24, and I28, whose salts with large, weakly polarizing cations such as CS and may be isolated. Organoiodine compounds have been fundamental in the development of organic synthesis, such as in the Hofmann elimination of amines, the Williamson ether synthesis, the Wurtz coupling reaction, and in Grignard reagents. The carbon-iodine bond is a common functional group that forms part of core organic chemistry. Formally, these compounds may be thought of as organic derivatives of the iodide anion. The simplest organoiodine compounds, alkyl iodides, may be synthesized by the reaction of alcohols with phosphorus triiodide. These may then be used in nucleophilic substitution reactions, or for preparing Grignard reagents. The Ci bond is the weakest of all the carbon-halogen bonds due to the minuscule difference in electronegativity between carbon and iodine. As such, iodide is the best leaving group among the halogens, to such an extent that many organoiodine compounds turn yellow when stored over time due to decomposition into elemental iodine. As such, they are commonly used in organic synthesis, because of the easy formation and cleavage of the Ci bond. They are also significantly denser than the other organohalogen compounds thanks to the high atomic weight of iodine. A few organic oxidizing agents like the iodines contain iodine in a higher oxidation state than 1, such as 2-iodoxybenzoic acid, a common reagent for the oxidation of alcohols to aldehydes, and iodobenzene dichloride, used for the selective chlorination of alkenes and alkynes. One of the more well-known uses of organoiodine compounds is the so-called Iodoform test, where iodoform is produced by the exhaustive iodination of a methyl ketone, as follows. Some drawbacks of using organoiodine compounds as compared to organochlorine or organobromine compounds is the greater expense and toxicity of the iodine derivatives, since iodine is expensive and organoiodine compounds are stronger alkylating agents. For example, iodoacetamide and iodoacetic acid denature proteins by irreversibly alkylating cysteine residues and preventing the reformation of disulfide linkages. Halogen exchange to produce iodoalkanes by the Finkelstein reaction is slightly complicated by the fact that iodide is a better leaving group than chloride or bromide. The difference is nevertheless small enough that the reaction can be driven to completion by exploiting the differential solubility of halide salts, or by using a large excess of the halide salt. In the classic Finkelstein reaction, an alkyl chloride or an alkyl bromide is converted to an alkyl iodide by treatment with a solution of sodium iodide in acetone. Sodium iodide is soluble in acetone and sodium chloride and sodium bromide are not. The reaction is driven toward products by mass action due to the precipitation of the insoluble salt. Iodine is the least abundant of the stable halogens, comprising only 0.46 parts per million of Earth's crustal rocks. Among the 84 elements which occur in significant quantities, it ranks 61st in abundance. Iodide minerals are rare, and most deposits that are concentrated enough for economical extraction are iodate minerals instead. Examples include laterite, Ca2, and diatsite, 7Ca28 Cacro4. These are the minerals that occur as trace impurities in the caliche, found in Chile, whose main product is sodium nitrate. In total, they can contain at least 0.02% and at most 1% iodine by weight. Sodium iodate is extracted from the caliche and reduced to iodide by sodium bisulfite. This solution is then reacted with freshly extracted iodate, resulting in comproportionation to iodine, which may be filtered off. The caliche was the main source of iodine in the 19th century and continues to be important today, replacing kelp, but in the late 20th century brines emerged as a comparable source. The Japanese Minami Kanto gas field east of Tokyo and the American Anadarko Basin gas field in northwest Oklahoma are the two largest such sources. The brine is hotter than 60 degrees C from the depth of the source. The brine is first purified and acidified using sulfuric acid, then the iodide present is oxidized to iodine with chlorine. An iodine solution is produced, but is dilute and must be concentrated. Air is blown into the solution to evaporate the iodine, which is passed into an absorbing tower where sulfur dioxide reduces the iodine. The hydrogen iodide is reacted with chlorine to precipitate the iodine. After filtering and purification, the iodine is packed. These sources ensure that Chile and Japan are the largest producers of iodine today. Alternatively, the brine may be treated with silver nitrate to precipitate out iodine as silver iodide, which is then decomposed by reaction with iron to form metallic silver in a solution of iron iodide. The iodine may then be liberated by displacement with chlorine. Unlike chlorine and bromine, which have one significant main use dwarfing all others, iodine is used in many applications of varying importance. About half of all produced iodine goes into various organoiodine compounds, another 15% remains as the pure element, another 15% is used to form potassium iodide, and another 15% for